For most of recorded human history, we thought our galaxy was the entire universe. Not part of it, not a fraction of it, all of it. Every star you could see with your naked eye, every faint smudge of light in the night sky, we assumed that was the complete inventory of everything that existed. One island, no shore in sight, no hint there was anything beyond it. We now know that assumption was wrong by a margin so large it's almost embarrassing. The observable universe contains an estimated 2 trillion galaxies. Our galaxy, the Milky Way, is one grain of sand on a beach so vast, we still haven't finished mapping it. But here's what should actually unsettle you. It's not just that we misunderstood the universe beyond our galaxy for so long. It's that we spent most of the 20th century unable to correctly map the shape, size, and structure of our own galaxy, the one we're literally standing inside of, right now, as you listen to this. We got the scale wrong. We got the shape wrong. We got our own position within it wrong. Repeatedly. Tonight, we're going to walk through exactly how and why humanity spent so long fundamentally misunderstanding the one galaxy we should have known best. And the answer reveals something almost poetic about the limits of trying to map something enormous from deep inside it, with no way to step outside and see the whole picture at once. Let's start with the first mistake, because it's the one that shaped everything after it, and it involves a scientist named William Herschel, working in the late 1700s, armed with nothing but a hand-built telescope and an extraordinary amount of patience. Herschel had a clever idea. If he counted the number of stars visible in different directions across the sky, he reasoned he could map the actual shape of the star system we live in. More stars in a given direction should mean the galaxy extends further that way. Fewer stars should mean the edge is closer. It was a brilliant method for its time, and using it, Herschel produced the first serious attempt at a map of our galaxy's shape, a flattened, disc-like structure, roughly similar in basic concept to what we now understand the Milky Way to actually look like. But Herschel's map had a critical flaw baked into it, one he had no way of detecting with the technology available to him. He assumed that all stars have roughly the same intrinsic brightness, and that dimmer stars were simply farther away. He also had no way of knowing that space isn't perfectly transparent, that vast clouds of interstellar dust scattered throughout the galaxy actually block and dim starlight, making distant stars appear fainter and therefore seem much closer than they actually are. The result was a galaxy map that placed our sun almost dead center of the entire structure, with the visible stars forming a relatively modest disk around us. It felt intuitive. It felt, in a very human way, comfortable Earth star sitting near the middle of everything. Once again, it was also completely wrong. And it would take more than a century to figure out exactly how wrong. The next major twist in the story arrived in the early 1900s, and it involves a debate so significant, so consequential, that historians of science still refer to it by name, the Great Debate. By this point, astronomers had discovered something curious in the night sky: faint, fuzzy, spiral-shaped smudges of light scattered among the stars, which they called spiral nebulae. Nobody knew exactly what they were, and there were two competing camps, each defending a fundamentally different vision of the universe's actual scale. One camp, led by astronomer Harlow Shapley, argued that these spiral nebulae were relatively small, nearby objects, existing within our own galaxy, and further, that our galaxy itself was truly enormous, roughly 300,000 light-years across, with our sun sitting far from its center, out toward the edges. The opposing camp, championed by astronomer Heber Curtis, argued something almost the exact opposite. Curtis believed these spiral nebulae were actually entire separate galaxies in their own right, vast island universes, as they were poetically called at the time, existing at staggering distances far beyond the boundaries of our own galaxy. Under Curtis's model, our galaxy was comparatively smaller, but the universe as a whole was almost incomprehensibly larger, filled with countless other galaxies similar to our own. On the 26th of April 1920, these two astronomers presented their competing cases publicly in what became one of the most famous scientific debates of the century. And here's the genuinely fascinating part. Neither man was completely right, and neither man was completely wrong. Shapley had correctly determined that our sun was not at the center of the galaxy, a genuinely important, previously unknown truth, using observations of star clusters called globular clusters to correctly estimate our real position within a much larger galactic structure than Herschel had imagined. But Shapley's estimate of the galaxy's overall size was too large, and he was wrong about the nature of the spiral nebulae, believing them to be part of our own galaxy rather than separate systems entirely. Curtis, meanwhile, correctly argued that spiral nebulae were separate, independent galaxies, a genuinely revolutionary insight that would eventually be proven true. But his estimate of our own galaxy's size was too small, and he still clung to an outdated assumption that placed our solar system relatively close to the galactic center. Two brilliant scientists, two carefully reasoned, evidence-based arguments. And both were tangled up in a mixture of real insight and fundamental error, because the tools available to them simply weren't precise enough yet to settle the question cleanly. It would take a few more years, and one of the most important astronomers in history, to finally break the deadlock. Her name was Henrietta Leavitt, and though she wasn't present at the Great Debate itself, her earlier work made its eventual resolution possible. Working at the Harvard College Observatory in the early 1900s, during a time when women in astronomy were routinely excluded from formal academic positions and relegated to painstaking, underpaid data analysis work, Leavitt studied a specific type of star called a Cepheid variable, which brightens and dims in a regular, predictable rhythm. Leavitt discovered something remarkable. The period of that brightening and dimming cycle was directly related to the star's true intrinsic brightness. Find a Cepheid variable star anywhere in the sky, measure how quickly it pulses, and you could calculate exactly how bright it truly is. Compare that to how bright it appears from Earth, and you could calculate with genuine precision exactly how far away it is. It's difficult to overstate how significant this discovery was. Leavitt had essentially handed astronomy a cosmic measuring tape, a reliable way to calculate real, accurate distances to faraway objects, for the very first time in history. In 1923, astronomer Edwin Hubble used exactly this method, pointing the largest telescope in the world at the time toward the Andromeda Nebula, one of those mysterious spiral smudges at the center of the Great Debate. Using Leavitt's technique, he identified a Cepheid variable star within it and calculated its distance. The results settled the debate decisively. Andromeda wasn't a nearby cloud of gas inside our own galaxy. It was roughly 2 million light-years away, an entire separate galaxy, comparable in scale to our own, existing far beyond anything Shapley or Curtis had fully imagined. The universe, in a single calculation, exploded in scale. We weren't the whole universe. We weren't even close. You'd think, after a discovery that monumental, that the remaining mystery, the actual shape and structure of our own galaxy, would have been solved relatively quickly afterward. It wasn't, and the reason why is genuinely fascinating, because it reveals something almost unfair about trying to map a spiral galaxy from inside one of its arms. Here's the core problem, and it's worth sitting with, because it explains almost every mistake that came after it. If you wanted to draw an accurate map of a city, it would help enormously to fly above it and look down. You could trace the streets, the layout, the overall shape, all at once, from a single vantage point. We can't do that with the Milky Way. We are embedded directly inside the galactic disk, roughly 2/3 of the way out from the center, looking out at everything else from within the structure itself. There's no way to fly above it and take a photograph. Every single piece of information we've ever gathered about our galaxy's shape has had to be pieced together indirectly through painstaking measurements taken from a single, fixed vantage point buried deep within the very thing we're trying to map. Making matters significantly worse, our galaxy's disk is thick with gas and interstellar dust, which scatters and absorbs visible light. Looking directly toward the galactic center in particular involves peering through roughly 26,000 light-years of dust, gas, and stars, enough obscuring material that, for centuries, we couldn't even directly see the galaxy's own core with visible light. It's a little like trying to determine the exact layout of a house while standing inside one of its closets, with the lights mostly off, and thick smoke filling most of the hallways. It wasn't until astronomers began observing in radio waves and infrared light, starting in earnest in the mid-20th century, that we finally gained the ability to peer through that dust. Radio waves and infrared light pass through interstellar dust far more easily than visible light does, which meant, for the first time, astronomers could begin tracing the actual structure of our galaxy's spiral arms, hidden gas clouds, and even the galactic center itself, previously invisible to us entirely. And what they found complicated things even further. Because here's a detail that surprises most people. We still don't have a complete universally agreed upon map of our own galaxy's spiral arm structure. Not in some vague historical sense right now, in ongoing active research. Different surveys, using different methods and different traces, young stars, gas clouds, or the newest, most precise data from missions like the European Space Agency's Gaia spacecraft have produced meaningfully different pictures of exactly how many major spiral arms our galaxy has and precisely how they're arranged. For decades, textbooks confidently illustrated the Milky Way as a four-armed spiral galaxy. More recent infrared surveys have suggested we might actually have only two major arms, with additional smaller, partial arm segments branching off between them, a genuinely significant revision to how the galaxy is typically depicted, and one that arrived only within the last couple of decades, well within living memory. This remains an active area of debate among astronomers, with new data continuing to refine, and sometimes directly contradict, previous conclusions. Think about that for a moment. We have detailed photographs of galaxies millions of light years away, capturing their spiral structure in exquisite, unambiguous clarity. And yet the precise shape of our own galactic home still isn't fully settled science. We can photograph other people's houses from across the street with more clarity than we can map our own from the inside. There's something almost humbling, even a little poetic, buried in that irony. Let's talk about another layer of this mystery, because it involves one of the strangest, most consequential discoveries in modern astrophysics, and it also happened to unfold right here inside our own galaxy. In the 1970s, astronomer Vera Rubin, working alongside Kent Ford, began carefully measuring the rotation speeds of stars at different distances from the centers of spiral galaxies, including our own, based on standard physics, and based on the visible amount of matter concentrated toward each galaxy's center. Stars orbiting farther out should move noticeably slower than stars closer, in the same basic principle that governs how planets farther from the Sun orbit more slowly than planets closer to it. That's not what Rubin found. Stars far out at the edges of galaxies were orbiting just as fast as stars much closer to the center. Far faster, in fact, than the visible matter in those galaxies could possibly account for through gravity alone. There were only two possible explanations. Either our fundamental understanding of gravity itself was incomplete, or there was a substantial amount of additional, invisible matter distributed throughout these galaxies, providing extra gravitational pull that we simply couldn't see. That invisible matter is what we now call dark matter, and Rubin's observations remain some of the most important evidence supporting its existence. Current estimates suggest our own galaxy is embedded within an enormous, roughly spherical halo of dark matter, extending far beyond the visible disk of stars we typically picture when we think of the Milky Way, and containing significantly more mass than all of the galaxy's visible stars and gas combined. We have never directly detected a single particle of dark matter, not once, in nearly 50 years of dedicated searching, using increasingly sensitive detectors buried deep underground specifically to shield them from interference. We only know it's there because of what it does, the way it shapes the rotation of our own galaxy, the way it bends light from objects behind it, the way galaxies across the universe simply refuse to hold together under gravity without something extra providing additional mass. Which means the honest, unsettling truth is this: we don't just misunderstand the shape of our own galaxy. We don't even know what most of it is actually made of. The majority of our galaxy's mass, right now, remains fundamentally mysterious, invisible, undetected, identified only by the gravitational shadow it casts on everything else. We live inside a structure that is, by mass, mostly composed of something we cannot see, cannot touch, and cannot yet explain. So how close are we, right now, to finally getting an accurate, complete picture of our own galactic home? Closer than we've ever been, and the reason involves one of the most ambitious mapping projects in the history of astronomy. In 2013, the European Space Agency launched the Gaia spacecraft with a singular, extraordinarily ambitious mission: precisely measure the position, distance, and motion of over 1 billion stars within our galaxy, creating the most detailed three-dimensional map of the Milky Way ever attempted. Gaia works using a technique called parallax, measuring the tiny, almost imperceptible shift in a star's apparent position as Earth orbits the Sun, viewing that star from slightly different angles 6 months apart. It's the same basic principle as holding your finger up and closing one eye, then the other, watching it shift against a distant background. applied with extraordinary precision across more than 1 billion stars. This technique has allowed astronomers to build a genuinely revolutionary map, one dense enough and precise enough to finally start resolving long-standing debates about our galaxy's true structure. Gaia's data releases, arriving in stages throughout the 2010s and 2020s, have already overturned assumptions that stood for decades. We've discovered that our galaxy's disk isn't perfectly flat, the way it's traditionally illustrated, but is actually gently warped and twisted at its outer edges, like a slightly bent vinyl record, likely due to gravitational interactions with smaller satellite galaxies orbiting nearby. We've uncovered evidence of ancient galactic mergers, written into the motion of stars still bearing the gravitational fingerprints of other, smaller galaxies that our own Milky Way consumed and absorbed billions of years ago. We are, quite literally, still discovering entirely new structural features of our own galaxy within the last several years, not centuries ago, not decades ago, but recently enough that some of the astronomers making these discoveries are the same people teaching university courses about galactic structure right now. So here's where this leaves us, and it's a genuinely strange place to stand. We've spent roughly 2.5 centuries from Herschel's first careful star counts in the 1700s to Gaia's billion-star map today, trying to accurately understand the one galaxy we actually live inside of. And in that time, we've been wrong about its size, wrong about its shape, wrong about our own position within it, wrong for a significant chunk of that history about whether it constituted the entire universe or merely one galaxy among countless others. And we're still actively revising basic details about its spiral arm structure, its outer warp, its ancient history of galactic collisions, and most humbling of all, we still don't know what most of its actual mass is made of. It's tempting to feel a little embarrassed by that track record. But there's a different, more generous way to look at the same set of facts. Every one of those mistakes wasn't a failure of human intelligence. It was a natural, unavoidable consequence of trying to map something enormous from deep inside it, using only the tools available at each moment in history: hand-built telescopes, star counts, pulsing variable stars, radio antennas, and eventually a spacecraft precisely tracking the subtle wobble of 1 billion distant suns. Each wrong answer wasn't a dead end, it was a necessary, load-bearing stepping stone toward the next, slightly less wrong answer. And there's something worth sitting with in that pattern, something that stretches well beyond just astronomy. We are, all of us, standing inside something too large to see all at once: a galaxy, a universe, a moment in scientific history squinting through the dust, measuring what little light reaches us, and slowly, patiently, generation after generation, building a slightly clearer picture than the one we inherited. We still don't have the final map. Not of our galaxy's precise spiral structure, not of the dark matter halo silently enclosing everything we can see, not of the countless smaller mysteries still hiding in Gaia's growing mountain of data, waiting for someone to notice them. But for the first time in human history, we finally know, with real confidence, roughly where we are. A modest, unremarkable star, about 2/3 of the way out from the center of a barred spiral galaxy, itself just one of 2 trillion galaxies, scattered across an observable universe 93 billion light-years wide. It took 2.5 centuries to get even that far. And the truly remarkable part is this: the same telescopes, the same spacecraft, the same relentless human curiosity that finally revealed where we stand are still running right now, still gathering data, still quietly rewriting the map beneath our feet. We finally know roughly where home is. We're still figuring out exactly what home actually looks like.